In this video, we are going to talk about another class of functions called exponential functions. And we will talk about their graphs, graph transformations, and also solve applications of exponential functions. So we've studied thus far polynomial functions like lines, parabolas, rational functions, 1 over x, 1 over x squared, square root functions like the square root of x. And in each of these cases, the variable was in the base, right? F of x equals x squared. The base of that exponential expression is x. F of x equals the square root of x is equivalent to x to the 1/2. So the base is the variable, even with f of x equals 1 divided by x. This is equivalent to x to the -1. So again, the base is in the variable. So those are algebraic functions. We're going to study a new class which are called transcendental functions, which are exponential functions, and it will be something of the form f of x is equal to 2 to the x. So note here that the variable is in the exponent, and these are again called exponential functions. The official definition is that an exponential function is a function of the form f of x equals b to the x for all real numbers x and for a real number b such that b is greater than 0 and b is not equal to 1. Right? If it was 1, 1 to the x is just 1, so that would actually be a constant function. If b is negative, then we might get into situations where our expression is undefined, like if b is -4 and our exponent is 1/2, that would be the square root of -4, which is an imaginary number. So we just want to safeguard against things like that. So here's our perhaps simplest exponential function, f of x equals 2 to the x. If we wanted to graph this function without having any idea of what it looks like, remember that we can choose values for x, substitute into the function, and find the corresponding y value. If we plug in -2, our y value then is 2 to the -2. But remember the definition of the negative exponent, that means to do 1 divided by 2 squared, or 1/4, which is 0.25. 2 to the -1 is equivalent to 1 divided by 2 to the 1, or 1/2, which is 0.5. 2 to the 0, well, remember anything to the 0 exponent is just 1. 2 to the 1 is equal to 2, and 2 squared is equal to 4. So when we plot these on a coordinate system, we can plot 2, 4, 1, 2, 0, 1, -1, 1/2, -2, 1/4. So observe that 2 to the x is never equal to 0. It doesn't matter what value of x I substitute into this function, I will never get 0. And we can see that graphically because we have this horizontal asymptote at the x-axis or at y equals 0. And so one characteristic of the graph of an exponential function is that it will have this horizontal asymptote at the value at which it cannot cross, and the value at which all the other y values are larger than. So key characteristics of the graph of f of x equals 2 to the x is that the domain is all real numbers, -infinity to infinity. I can plug any number, any real number, into the function and get an output value that is a real number. I can even find like 2 to the square root of 3. Right, your calculator can do that. The range, note that my graph is all above the x-axis, so that means it is open parentheses 0 to infinity, close parentheses. Do I have an x-intercept? No, because the graph never crosses the x-axis. My y-intercept is the point 0, 1. The horizontal asymptote, remember that is always an equation of a horizontal line, which is y equals 0. And then two things I know about this function is that as I move from left to right, notice that my graph is increasing or rising, so we can say this is an increasing function. And also, if I do the horizontal line test, I find that this is also a one-to-one function, which means that it will have an inverse, which we'll talk about later. And then the other thing I want to think about is this end behavior to the left. So we say as x goes to negative infinity, remember that means as I'm going to the left end of my graph, what is happening to the y values? Well, notice that the points are all approaching this x-axis, which is a y value of 0, right? They're approaching that horizontal asymptote. So we said that y approaches 0. Now this is not true at the other end. If we say as x goes to positive infinity, well, y is actually approaching infinity there, right? Because on the right end, my graph is going up infinitely. Now what if we want to look at the graph of f of x equals 1/2 to the x? So now my base is a number that is between 0 and 1. So if I plug in -2 to this function, 1/2 to the -2, remember this fundamental rule of fractions, if I have a divided by b raised to the -n, that is equivalent to b divided by a to the n. So I can take the reciprocal of my base and make the exponent positive. 1/2 to the -2 is actually equivalent to 2 divided by 1, or just 2 squared, which would be 4. 1/2 to the -1 is equivalent to 2 to the 1, or 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2, or 0.5. And then 1/2 squared, 1/2 times 1/2 is 1/4, or 0.25. So when I plot these on a coordinate system, notice that I have -2, 4, -1, 2, 0, 1, 1, 1/2, and 2, 1/4. So again, I find that the output is never equal to 0. So I see that, again, this line y equals 0 is a horizontal asymptote of the graph. When I think about some key characteristics of this graph, notice that my domain is still all real numbers because the graph continues infinitely from the left to the right, so it's negative infinity to infinity. The range from bottom up, the y values are all positive, so it would be from 0 to infinity. The x-intercept, well, there is none, again, because the graph does not cross the x-axis. My y-intercept is the ordered pair 0, 1. The horizontal asymptote is y equals 0. Now this time, as we read from left to right, the function is declining or going down, and so we say that this is a decreasing function. But it also passes the horizontal line test, so this is a one-to-one function. As far as the end behavior, as x goes to infinity, so this means the right end of my graph, what are the y values doing? Well, all of those points are getting closer and closer to this line y equals 0, which tells me that the y values are approaching 0. If we want to fill in the other behavior as x goes to negative infinity. Well, on the left end of my graph, what is the graph doing? It's going up, infinitely up. So that means that the y values are going to infinity. And I want you to also recognize that the graph of 1/2 to the x is a reflection across the y-axis of f of x equals 2 to the x. And we can see that because we can rewrite 1/2, that is that base, as 2 to the negative 1, all raised to the x. And remember rules of exponents. When you have an exponential expression raised to another exponent, you can multiply those exponents. So 2 to the negative 1 all to the x is actually equivalent to 2 to the negative x. So we see that when we compare y is equal to 2 to the x and y is equal to 2 to the negative x, that there is a change attached to the x, which is we're taking the opposite of the x, which we saw in section 11 was a transformation that resulted in a reflection across the y-axis. So some general characteristics that we want to state of the graph of f of x equals b to the x is that the base of the exponential function determines its general shape. If the base of the exponential function is greater than 1, then the function is increasing and models exponential growth. Right? Think about the growth of bacteria, the growth of viruses, those types of things. If the base of an exponential function is between 0 and 1, the function is a decreasing function and models exponential decay. We're going to talk about applications of that later on, like the deal with half-life of radioactive isotopes. But so if the base is greater than 1, increasing growth, between 0 and 1, the function is decreasing and exponential decay. So the basic shapes of the graph of y equals b to the x for b greater than 1, notice that we have this horizontal asymptote at y equals 0. The graph will always go through the y-intercept of 0, 1, and it's increasing from left to right. So this is an increasing function. The domain is all real numbers, negative infinity to infinity. The range is 0 to infinity. The horizontal asymptote is y equals 0. And it passes through that key point of 0, 1. Now when the base is between 0 and 1, the graph is a decreasing function. It goes through the key point of 0, 1. The domain is still all real numbers, negative infinity to infinity. The range is 0 to infinity. And the horizontal asymptote is the equation y equals 0. A very important exponential function in applications related to finance, growth models, and the study of calculus is the natural exponential function defined as f of x equals e to the x. The base of the natural exponential function is e, and e is actually an irrational number, just like the number pi, for instance, but e has a value that's approximately 2.71828. So I can use my calculator to figure out what are the output values of this exponential function when the base is e. And I have a slide in just a minute that's going to show you how to use your calculator to get the base of e. But if I want to figure out what e squared is on my calculator, I can do that, and e squared is about 7.4. I'm just going to round to one decimal place. So y is e squared, which is approximately 7.4. When we have the input of 1, e to the 1 is approximately 2.718, so we'll just say 2.7. When x is 0, we get e to the 0, which is just 1. And when the input is -1, e to the -1 is 1 divided by e, or about 0.4. And then when we have e to the -2, that's really 1 divided by e squared, which is about 0.1. So notice again that the things that we just learned about the exponential function hold true. 0, 1 is going to be the y-intercept, and then none of the output values are 0, right? They're all positive. So we can graph this function on a coordinate system. We can see that it goes through the point 0, 1, it goes through the point 1, 2.7, and then it goes through 2, 7.4, -1, 0.4, and so on. So where does this number e come from? The number e actually comes from the limit as n goes to infinity. So think about that arrow notation that we used to have as x goes to infinity. So we're thinking about as n goes to infinity, what is the value of this expression 1 plus 1 divided by n, all raised to the n? And that limiting value is the number e. So I put this on the calculator and I've captured some screenshots. I put in that expression 1 plus 1 divided by x, all raised to the x. I put in to y2 just the value e, so that's the graph of y equals e, which is just a horizontal line through approximately 2.718. And I see that my graph as I go to the right, that is as I go to infinity, the graph of this function is approaching that horizontal asymptote of y equals e. So that is the limiting value that this is approaching is the value e. I also looked at the table and I input really, really large values of n, like 5100, 5200, 5300, up to 6000, 6100. And when I arrow over to the y column, I see that my value is like 2.718, right? And if I keep increasing, it's going to continue getting closer and closer to that 2.71828 value that we define e to be. Now, how do you access e on the calculator? There's two ways. E to the x is in blue above this ln key, which we'll talk about in the next section. But so I could do second in ln, and that gives me e with an exponent, so then I could type in whatever exponent I wanted to. Another way is actually to just type in the base e. I can do second and the division sign. Do you see right above the division key in blue is the number e? So if I do second division, I get e, and if I press enter, I see what its value is equivalent to. And then if I wanted to graph e to the x, I can press my y equals key, type in second ln to get the e, and then I can enter x into the variable exponent, and then press enter, and then I can graph it to see the function that we just drew by hand. And then I can do second table to get the values that we also just calculated. So as just one quick example we're going to do for this objective, and that is to graph these basic functions f of x equals 4 to the x and f of x equals 1/4 to the x. And we want to state the domain, range, intercepts, and asymptotes of each function, and state whether the function is increasing or decreasing. So if we wanted to graph y equals 4 to the x, we would need to make a table. And we can plug in values like -2, -1, 0, 1, and 2. And then the output would be 4 to the -2, which is 1/4 squared, or 1/16. 4 to the -1 is 1 divided by 4, or 0.25. 4 to the 0 is 1. 4 to the 1 is 4, and 4 squared is 16. So we can plot these points. 1/16 is 0.0625. So negative 2.06, that is almost touching 0 there. Negative 1.25 is a fourth way up. 0, 1 is on my y-axis. 1, 4, and then 2/16 is going to be way off my graph, but we can see the basic shape. It's going to be going from left to right, rising through these points. And it's going to be steeply increasing. And so we can state these things. The domain of that function is all real numbers, negative infinity to infinity. The range is from 0 to infinity, because my output is never negative. We have a horizontal asymptote at y equals 0. And because the base is 4, the function is increasing. And one other thing, the y-intercept is the point 0, 1. There is no x-intercept. And then if I wanted to graph y is equal to 1/4 to the x, I can make my same table, choose values of negative 2, negative 1, 0, 1, and 2. 1/4 to the negative 2, remember that's just 4 squared or 16. 1/4 to the negative 1 is 4 to the 1 or 4. 1/4 to the 0 is 1. 1/4 to the 1 is 1/4 or 0.25. And then 1/4 squared is 1/16. And like we just saw, that's 0.0625. So when I plot these points, negative 2, 16, again, it's going to be way off my chart. Negative 1, 4 is in the second quadrant. 0, 1, 1.25, and 2.0625, which is hard for me to draw because it's so close to the x-axis. So now I'm going to draw the graph through these points, showing that I'm getting closer and closer to the x-axis as I go to the right. So this time my domain is still all real numbers, negative infinity to infinity. Range is 0 to infinity, right from bottom to top. Horizontal asymptote is still at y equals 0. This time, because the base is between 0 and 1, this is a decreasing function. I have a y-intercept at 0, 1, and there is no x-intercept. Now, of course, you could do this on the calculator. I have some screenshots that I've captured here. In your equation editor, when you press y equals, you're going to enter 4 and the exponent key and then the xt theta to get the variable key. You can graph it to see the same shape that we just showed by hand. And then I can also press second graph to get to a table of ordered pairs. Likewise, I can do in parentheses a base of 1/4, the exponent key raised to the x. Graph, I see this decreasing function that approaches the horizontal asymptote of y equals 0. And then I can look at my table, second graph, to see those values that we just obtained by hand.